Hello, everyone. Thank you for your patience. We will now begin the program. Thank you very much for joining us today for the Kyoto University Center for Cancer Immunotherapy and Immunobiology, CCII in short, New York lecture, titled Nobel Prize-winning Immunotherapy in Cancer Treatment. We are very grateful to have many participants joining us both in person and virtually. My name is Nanako Tojo, the project manager of Friends of Kyoto University North America branch. It is my honor to be your moderator today. In the US, approximately 5,800 people are newly diagnosed with cancer every day, and about 20 people lose their lives to the disease daily. To understand how large the numbers are, I'd like to draw the number of daily deaths in the US during the peak of the COVID-19 pandemic. It ranged from 3,000 to 4,000. This means the toll of cancer has persisted for a long time at a scale nearly half the pandemic peak, a truly serious reality. In the face of these challenges, immunotherapy has emerged in recent years as a transformative innovation in cancer treatment. As you may know, the 39th US President Jimmy Carter also achieved a full recovery from cancer through this immunotherapy, bringing hope to people everywhere. The purpose of this event is to present you the front lines and future of cancer research, specifically immunotherapy, directly from leading scientists. We also aim to introduce the initiatives of Kyoto University CCII, Japan's first dedicated cancer immunotherapy research hub. It is founded by Dr. Tasuku Honjo, the 2018 Nobel laureate, who developed immunotherapy drugs now used worldwide. Ultimately, we hope to expand international collaboration and support for this vital research. So let's start. First, we would like to introduce the activities of Kyoto University CCII through a video.
Hello everybody, I Tasuku Honjo, serving as the director of CCII. CCII brings together under one roof researchers and physicians who try to understand the basic principles of immunobiology and improve cancer immunotherapy for future generations.
Kyoto University has a long, successful tradition in medical research. Professor Honjo's cancer immunotherapy research has transformed the lives of many patients. It began here 30 years ago with a basic research question. Our new Cancer Immunotherapy Center will become a symbol for Kyoto University and its Faculty of Medicine. The CCII building was designed by visionary architect Mr. Tadao Ando.
Immunological checkpoint inhibitor therapy has saved thousands of lives, but cancer remains a tragedy for countless patients and their families. To advance immunotherapy, we must enhance our understanding of immune system regulation in depth.
To understand the immune cell function We absolutely need to understand the metabolism, the biochemistry of immune cells. So therefore, metabolism is a keyword for CCII, and many groups are trying to identify such metabolic pathways that will allow us to manipulate the immune system and also to find the cancer vulnerabilities and to exploit those vulnerabilities.
We'll continue our efforts to conquer cancer. We believe that life-saving treatments will emerge from this center. Thank you for your attention.
I hope the video provides you with a big picture of what CCII is doing. We are very proud of being the first research hub for cancer immunotherapy that the Nobel laureate Dr. Tasuku Honjo has pioneered, as well as driving world-class scientific advancement. Next, we'd like to share a video message from Dr. Honjo.
Welcome to the Kyoto University CCII webinar. I, Tasuku Honjo, now serve as the director of CCII. We developed cancer immunotherapy targeting PD-1, now used worldwide as Opdivo or Keytruda. This treatment originated from our 1992 discovery of PD-1. We eventually realized that PD-1 is a brake of the immune system, and blocking this brake could boost the body's power to fight various diseases, including cancer. Following extensive animal studies, the drug was first approved in 2014. Since then, it has saved millions of lives. However, immunotherapy is not almighty. Some cancers and some individuals remain resistant. To overcome these barriers, we are now pursuing various strategies to enhance immune cells, such as using anti-aging compounds like spermidine and mitochondrial activators. Although translating basic research into clinical use is a long and costly journey, CCII is determined to solve major cancer-related problems by 2050. Our goal is ambitious but realistic, driven by our talented team of scientists and clinicians. I sincerely hope you can support our approach by any means possible. Thank you for your attention.
Thank you for your attention. I believe that the message again highlights the profound impact of Dr. Honjo's breakthrough in cancer immunotherapy using the power of immune system, as well as the critical need for continuing this research. Moving forward, we'll hear from two leading researchers representing Japan's premier immunotherapy hub, Kyoto University CCII, and one of the leading cancer centers in the US, the Memorial Sloan Kettering Cancer Center. The two front runners in cancer research will discuss the latest research trends and prospects. Our first speaker is Dr. Kenji Chamoto from Kyoto University CCII. He will discuss the discovery of cancer immunotherapy, current research, and outlook for the future. Please join me welcoming Dr. Chamoto.
Hi, good morning, everyone. Thank you for coming here today. And my name is Kenji Chamoto from CCII, Kyoto University. So I would like to today to present the summary of PD-1 blockade therapy history and want to introduce our work in CCII. So as the previous video explained, PD-1 is expressed on the activated T cells, and PD-1 the role of PD-1 is to break the activated T cells. And tumor express a lot of PD ligand 1 and press PD-1. So T cell cannot activate and cannot attack the tumors. But PD-1 antibody block this PD-1, PD-L1 pathway, and the T cell reactivate again and can kill the tumors. And by this concept, Dr. Honjo was awarded the Nobel Prize at 2018. And in the case of the melanoma, before the PD-1 blockade therapy, the 5 years survival rate was less than 10%. But after the application of PD-1 blockade therapy, the 5-year survival rate reached to 44%. And it is noticeable that the patient who were resistant to the previous conventional therapies like chemotherapy, radiation therapy, change in such a patient, the cancer completely gone by PD-1 blockade therapy. So based on these evidences, the many companies now has developed their own PD-1 or PD-L1 antibody, and these were all applied to more than 20 type of cancers. And then now the PD-1 blockade therapy is the core of the cancer treatment. Okay. And let me briefly introduce how this PD-1 blockade therapy discovered. So PD-1 molecule was discovered around 30 years ago. Dr. Ishida and Agata was the student in the Honjo's laboratory at this time, and they subtracted the genes which is expressed in activated T cells and non-activated T cells. And they find PD-1 molecule is highly activated in the highly expressed in the activated T cells, and they determined the amino acid sequences. And they realized that these sequences, in some part, they are very similar to the previously known immunomodulatory molecules. So they believe PD-1 also has the immune functional role. And they continue to find the role of the PD-1 molecule. However, it took 10 years to know the function of PD-1. They developed the PD-1 knockout mice, and then they found finally these PD-1 knockout mice generate spontaneously the autoimmune diseases. It's very interesting that these PD-1 knockout mice generate in different organs their inflammation. For example, in the case of the B6 mice, black mice, they generate inflammation in the kidney, or in the case of bulb C mice, the heart is going to be inflamed. So strain difference is very obvious in these knockout mice. And this is the same case in human. PD-1 blockade therapy sometimes cause the side effect, which is called immune-related adverse event, IRAE, in a patient. But it's very, it is not yet known which patient this IRAE happens and which organ this inflammation happens. So this is the very important question in the science, in the cancer immunology field. Okay, let's get back to the history again. And because the PD-1 knockout mice cause the autoimmune diseases, and they found the PD-1 is the immune suppressive molecules. They hypothesized that this PD-1 may be used in the cancer development. So Dr. Minato and Dr. Honjo, Dr. Minato is now the president of the Kyoto University, developed their own PD-1 antibody or PD-1 antibody. And they injected in tumor-bearing mice, and then they found the tumor growth is inhibited significantly. And that was the 2002, but this paper is very important for the determination of the Nobel Prize. So they then tried to apply this concept to the clinical study. However, in Japan or in the world, most of people do not believe that immune cells can attack the tumors. So in Japan, Dr. Honjo tried to collaborate to the several, or no, most of the pharmaceutical companies, but ignored. So no choice. He asked the Medalex, which was the venture company in US at that time. And this Medalex has the experience of the development of CTLA-4 antibody. So Dr. Honjo decided to collaborate to this company. And then later, this Medalex was bought by the BMS. And then BMS started their PD-1 blockade therapy clinical study from the 2006. And in Japan, the collaborator Ono Pharmaceutical Company started the clinical study in 2009. And then the result was obtained first, 2012. But the result was amazing. In this clinical study, lung cancer and melanoma and renal cell cancer patients are included, but they are all resistant to the previous conventional therapies. But even in this late stage of patient, these percent of the patient become response to the PD-1 blockade therapy. So this study prove PD-1 is very important and prove that immune cells and T cells can attack the tumors in human. So then many pharmaceutical companies start develop their own PD-1 and PD-L1 antibody, and situation totally changed. So however, it's 10 years has passed since the first approval of PD-1 blockade therapy, and we know now PD-1 is very important, but two main issues remaining. One is the about half of patients that depends on the tumor types, but overall more than half of patients are still unresponsive. And we don't know what's the very critical biomarker which can distinguish the responsive and non-responsive patient to the PD-1 blockade therapy. So we need basic research to clarify this. And actually, many cancer researchers or immunology researchers worked on this, but it's very difficult to identify and solve these questions because the killer T cells, which is the main player of the cancer immunotherapy, is their function is regulated by so many factors. For example, cancer types or cancer antigen types, which is recognized by immune cells, and the tumor mutation numbers, we call tumor mutation burden. This is also control the T cell function quality and quality. And also, even immune cells, they are not always help the anti-tumor immunity, but they sometimes go to the immune suppressive cells. For example, immune suppressive macrophages or immune suppressive regulatory T cells suppress these killer T cells. So, and the tumor microenvironment is more complicated. Tumor vascular, mitochondria, and metabolism, and pH, and low concentration of oxygen. These many factors control T cell function. And even body environment is very important. So gut microbiota and aging, diet also control the killer T cell function. In the case of microbiota, the fecal transplant from responsive patient to unresponsive patient change the responsibility of the unresponsive patient. So if that transplant successful, the unresponsive people change to the responsive. And also aging is very important. In the COVID-19, we know in the COVID-19 vaccination, elder persons, the vaccination doesn't work. So that means immune power is declined in the elder persons. And it's reported that plant fiber taking people tends to be responsive to the PD-1 blocker therapy. So many factors control the T cells. So we need to combine everything together and think what's the anti-tumor immunity. So today I want to introduce our study on controlling T cell mitochondrial metabolism in aging background. So I need to introduce the T cell deterioration. So T cell is coming from the thymus, a very fresh state. And if they recognize tumor antigen, they differentiate into the effector T cells. This effector T cell is most important for the anti-tumor immunity, and they are going to be dysfunctional if they recognize tumor antigen more. And we call this one exhausted T cells. But finally, they are going to be die by apoptosis. So this arrow cannot be reversed. They just born freshly and they are going to be differentiated and they underwent deterioration. So this deterioration is boosted by many factors, for example, chemotherapy and aging, and also PD-1 blocker therapy. So PD-1 is expressed on effector or these dysfunctional T cells, and PD-1 blockade can temporarily recover these dysfunctional T cells. And the patient who can cure at this stage, that's fine, but many people cannot. And this important effector T cell is going to be differentiated, and most of them are going to be die. So the number of effector T cell reduced by PD-1 blocker therapy, and that is the one of the unresponsive to the PD-1 blocker therapy. So important strategy we found was to delay this speed of differentiation or deterioration. And the key strategy is the mitochondrial metabolism modulation. So our concept is that modulation of mitochondria in T cells. So the role of mitochondria is to produce the energy, but at the same time, that energy metabolism can change the T cells survive longer. So they are resistant to the apoptosis, cell death. So they can survive longer if mitochondrial metabolism is activated. So we screened the small molecules which can activate mitochondria. And we found a lot of these small molecules can enhance the PD-1 blockade therapy. Among these, today, I want to introduce two molecules, bezafibrate and spermidine. Bezafibrate is a ligand of PPAR, PGC1 alpha complexes, so you don't need to remember today this one, but this pathway is very important for mitochondrial activation. And bezafibrate is also long used as a drug for hyperlipidemia in the clinical. So if we combined the PD-1 blockade therapy with the bezafibrate, we can enhance the anti-tumor activity. PD-1 blockade alone is like this, but combined with bezafibrate, the tumor growth is shrinking much more, and their mouse life was extended. And at the same time, if we see the T cells in vivo, the T cell mitochondria activity is actually upregulated by the bezafibrate combination therapy. So we applied this concept to the human, and we conducted nivolumab PD-1 antibody, nivolumab and the bezafibrate combination therapy in the phase 1 clinical study. This is the, we recruited 18 patients of lung cancer patient. And we measured median PFS, which is one of the indicator of the survival. And their median PFS was 2.7 months. This is the very similar previously reported PD-1 blockade therapy alone. But we realized that this patient contains a lot of EGFR mutation positive patients who are known the resistant to the PD-1 blockade therapy. So we excluded these EGFR mutation positive and focused on EGFR mutation negative patient. And we found median PFS is 7.2 months. So in the previous report, in the same background, PD-1 blockade therapy alone is median PFS is 2.3 months. So bezafibrate combination extended survival around 3 times longer. So this is phase 1. So we cannot say significance, but this is very promising data. And we are motivated to go to the phase 2 clinical study. And during this therapy, we isolated killer T cells, CD8 positive killer T cells from patient blood. And we checked the expression of genes. And we found many genes were upregulated by the bezafibrate combination therapy compared with the nivolumab therapy alone. And these genes were mostly metabolic, associated with metabolic process or biosynthetic process. So even in the peripheral circulating killer T cells, this bezafibrate changed their phenotype, and they activate metabolism, and leading to the enhancement effect of the PD-1 survival rate. So we are now working on the phase 2 clinical study preparation. Okay, next is the spermidine. So spermidine is a very interesting molecule. Spermidine is like this structure, and they are called polyamine. And this spermidine polyamine exists in a body and the cells, organs, anywhere at the millimolar order. So it's very high concentration. But spermidine, the role of spermidine is anti-aging. If we administrate this spermidine in animals, that animals' life extended. And also spermidine has the anti-inflammatory effect, and that is good for Alzheimer or atherosclerosis. But unfortunately, this spermidine level is getting lower by aging in our body, even in urea. So we next investigated and summarized this top journal of 15 reports. The aging is important for the PD-1 blockade therapy as well. So we found that these several type of the cancers, the more than 15 years old or 17 years old patient tends to be unresponsive to the PD-1 blockade therapy. So aging should be very important. But in human, their genetic background or lifestyle is very heterogeneous. So we couldn't cut off clearly 75 years old or something. But in the case of mice, this trend is much clearer. Because in young mice, PD-1 blockade therapy works very well. But in aged mice, in the same tumor, same therapy, PD-1 blockade therapy doesn't work at all. But if we administrate spermidine, this anti-tumor immunity recovered. That means age-derived immune suppression or immune power reduction is recovered by spermidine administration. And their survival is extended. So molecular mechanism, it's very complicated. So I just summarize in this one slide and simply. So what we found was the spermidine binds to the mitochondrial protein directly, and the spermidine activate mitochondrial metabolism. And unfortunately, the T cells were aged, and their spermidine level is reduced. That's why mitochondrial metabolism is reduced, and then energy production was also reduced, and T cell function is declined. But after the supplementation of spermidine from outside, their spermidine level is increased in the mitochondria, and that enhanced the mitochondrial function and energy production, and their T cell function recovered. And then we proved that the anti-tumor immunity recovered even aged situation. So we are now focusing on this aging and T cell mitochondria, but in near future, maybe a lot of combination therapy will occur. The current combination therapy mostly based on the chemotherapy, molecular targeting therapy, and radiation. These days, now the combination therapy with angiogenesis inhibitor was approved. But from now, many of these drugs, for example, eliminating immune suppression or the drugs which can moderate immune metabolism, or the drugs or molecules which can change our body environment, including microbiota or anti-aging drugs. So these molecules which can change the situation or quality of T cells will be a good combination target rather than this conventional one. So next speaker, Guido, will explain the immune cell interaction, the interaction of cancer cells and immune cells. And he will present his own aspect and strategy. So finally, I'm a member of CCII, and CCII is the first institute in Japan to target the cancer immunotherapy. There is many institutes which target the cancer or immunology, but it's first to target cancer immunotherapy. So as we wrote in the homepage, our aim is this one. By 2050, broadly applicable immune intervention will enable control of nearly all cancers. And we are running to this goal now. So we kindly ask your continuous understanding and support. Thank you very much.
Thank you very much, Dr. Tamoto, for such an informative presentation. So for online participants, thank you for sharing some of your questions. Please keep posting questions. We will take some questions at the end of this evening. So our next speaker is Dr. Guido Wendell from the Memorial Sloan Kettering Cancer Center. He will speak about the current cancer research in his US-based lab and the potential for new cancer treatments. So please join me welcoming Dr. Wendell to the stage.
Ohayo gozaimasu. Thank you very much for having me. I'm having a great time with the friends of Kyoto University. So my lab is focused on cancer, how cancer responds to therapies. We try to develop new cancer therapeutics. One aspect of that is, of course, immunotherapies, because they really changed the way we treat cancer, the way we think about treating cancer, and give us ideas about new combinations moving forward. So the cat and mouse game between the cancer and the immune system, it has moved to the next stage. With the invention of PD-1, Kenji just showed you a great talk. It really changed the game of how we treat cancers. I'll just give you one sort of brief introduction slide to that topic. Just very briefly, Kenji just told you all of this. PD-1 expressed on the PD-L1 expressed on a cancer cell, PD-1 expressed on a T cell. This interaction is a way in which a cancer cell can defend itself against T cells. So the antibody disarms the tumor. It takes away the shield, if you will, and it makes it, unable to switch off an attacking T cell. And that is a great breakthrough. Now, if you're a scientist, you wonder, what's next? Where are we going to go next? So I look at the slide and say, well, you put 2 or 3 receptors on it. Maybe there's more receptors we should think. Well, we put T cells on it. Well, what about other cells that might be in the tumor environment that we might be able to activate, use for our therapeutics? And I'll give you some examples of the way we think about this in my lab. Just very briefly, a random survival curve. The impact is amazing. And I think this is in melanoma, PD-1 treatment. The most important data isn't on it. When I worked as a doctor in Germany several years ago, before PD-1, the survival was under 12 months. So there would be a red curve that stops somewhere, right? There is a massive shift in the way patients respond with this new therapy. It's really a game changer here. So I think that needs to be stated. Okay. Now, what are the issues now? Well, we can look back at this, and you can see we have long-term survival for several years in about 40% of patients. There are 60% where we don't achieve that yet. They live longer, but the disease isn't cured and they escape. So what are limitations? Kenji looks at this from the point of view of the immune cell. How do we make the immune cells better, right? Benzofibrate, spermidine, ways to make the T cells more active. I look at it from the other point of view of the cancer cell. I want to understand, how does the cancer cell escape? How can we prevent it from escaping? How can we make the cancer cell more sensitive to begin with? How can we mess with the cancer to make this therapy even more effective? So how my lab interest here is, how do tumor cells escape from these powerful immunotherapies? What are the mechanisms they escape? And many times, if you gain an advantage in one way, that gives you a disadvantage in a different way. What is the cost of escaping? What does it create new vulnerabilities? If a tumor learns to escape from PD-1, does it maybe now depend on a different immune checkpoint that we might want to target? Now, I'm going to give you 3 examples from work in our lab that just, I made them very, easy to understand, I hope. Just giving you key pieces of data, new ideas of the way that we think about this. And the first one is to talk about the different type of immune cells, and these are macrophages. Just a few slides to illustrate the point. Much of the work is in lymphoma. It's a disease that we're particularly interested in. The last one is actually in melanoma as well. The second is about recruiting T cells against cancer. And in fact, the person working on it is here. This is Kars back here from my lab. And the third is targeting a different immune checkpoint. PD-L1, PD-1 is one immune checkpoint. We think it's not the only one. There are backup mechanisms that allow cancers to defend themselves, and I'll tell you a little bit about this. So the first story is about macrophages that attack and eat tumor cells. The person working on this is a Spanish guy. His name is Javi Francisco de la Rosa Fernandez Pacheco. I hired him because he had the longest name of all the applicants. He's a very smart person. So macrophages, if you're not familiar with it, are a type of cells that can attack other cells and physically eat them, incorporate them. They basically eat them. We call the process phagocytosis. That's what macrophages do. They can, and this is very relevant in the context of maybe viral infections. The cell is infected with virus and it gets removed in this way. Macrophages can also attack cancer cells, and this is especially important, I think, in lymphomas, and I'll tell you a little bit about it. So this is then the interaction of a cancer cell up there in pink with a macrophage. And again, the cancer cell has developed a mechanism to defend itself. And the mechanism is a different receptor. It's called CD47. It is the so-called don't eat me receptor. Very easy. Don't eat me. Don't, stay away. Okay, so they protect themselves through this do not eat me receptor. Now, a group of Weizmann colleagues, Stanford, developed antibodies that block this receptor. The system is quite similar to what you just heard about PD-1, PD-L1. So we are blocking CD47, and suddenly the macrophage is now able to attack and to eat the tumor cells. Eat me. And this is actually very striking. This is just cells on a dish. This is what got me interested in macrophage. This exact picture, this is what his data in the lab. What you're looking at in red are the lymphoma cells in a culture, and at the bottom you see a few gray cells, and those are the macrophages. And the first is before we add the antibody, and on the right side, this is 24 hours after adding the antibody. And what happened is the macrophages have ingested, they've eaten all of the lymphoma cells. In many cases, you can still see the red lymphoma cells in the macrophages. So I thought this is such a powerful therapy, we should study this. In fact, the same is true if we do this in animals. These are mice with big angry lymphomas. and we treat them with a single injection of the antibody, just one single injection. And the red curve tells you how we can control the growth of these tumors. At the bottom, you actually see these ugly tumors, and some of them are completely gone, some there's still something there. But the therapeutic effect of this is very striking. Now, this treatment, full disclosure, has been unsuccessful in some cancers. Myeloid leukemias, as a single treatment, it had no survival benefit. It didn't do anything. In lymphomas, it's very promising. And there's a specific reason to it. Lymphomas are very sensitive to this macrophage attack mechanism. Now, we wanted to understand in the lab, how can, if this treatment is so effective, and in very early clinical trials, you get responses of 90% or so of lymphoma patients. Well, how can we reach the rest? How can we make it even better than this? What can we do about the tumor? And we use something that's called CRISPR. You've heard of CRISPR as a gene editing tool. And the way we use it is we use CRISPR libraries where we target every gene in an individual cell. And then we treat them and we ask which of those cells have survived, which mutation has allowed them to escape the treatment. And that's what you get. You get a number of different hits there. I won't go into the details of it. One thing that stood out to Javi is a lipid metabolism pathway. And in fact, his screen found, you see in green, these are the abbreviations of enzymes in this one pathway. And he found 4 consecutive enzymes in a specific fatty acid synthesis pathway. And if you see a pattern like this, you have to say, well, there must be something to this. There must be some truth to this. We've tested this and retested it, and yes, it is true. The key enzyme here is at the top of it is called ELOF-L6. This is an elongase. An elongase means it extends carbon chains by 2 atoms. So this one goes from 16 to 18 atoms. And if you look at the lipids in these lymphoma cells, what does ELOF-L6, if tumor cells don't have it, what changes? This is what changes. You see that everything that has an 18 is on the left side, which means it's decreased. They're unable to produce different C18. And everything with a 16 is on the right side, which means they try to make more of that. They're stuck. There's a block in elongating 16 to 18. Okay. Now, one of the key fatty acids here, there are really 2, stearic acid and oleic acid. Those are the 2 that are missing, and they're missing in synthesizing membranes and other cellular functions. Now, what happens if we fix this problem by simply supplementing, as you just talked about spermidine, by simply supplementing oleic acid? Now, oleic acid is the chief ingredient in olive oil. We find just in tissue culture, in cells, it restores the phagocytosis. It changes the way CD47 is presented on the membrane. I'm not going to go into details. And the same is true in animals. So if the treatment with a diet enriched, we just dunk the chow in olive oil, improves the therapy of this antibody significantly. I'm not going to go into all the mechanistic detail. It's just a very simple, it's an interesting finding that tells you that, simply what we eat, our diet, actually has an effect on how our immune system works, and it has an effect on how tumor cells interact with the immune system. And this specific enzyme is very interesting for being needed for sensitivity to macrophages and to antibody therapies in lymphoma. Yeah. So I'm excited about it. We just wrote the paper. We're submitting it basically this weekend if Javi gets his act together. And so that I hope we'll get it published soon. So the second story, this is Kazuya Fukusawa. He is right here. He goes by Kaz. He is teaching me Japanese. And an excellent postdoc in the lab. And I think he's dreaming of CCII. This is a big aspiration of us. So Kaz works on T cells, and he has a very interesting project. Now we have, in the clinic, we have 2 different ways of recruiting T cells into tumors. You want to bring the T cell to the tumor. Now, one is making CAR T cells. You might have heard of this. you express a receptor like CD19, CD20 receptor on the T cell, and then the T cell is able to go to the tumor, attack the tumor, and it works. The other way of doing it, we use something called bispecific antibodies. These are antibodies that have two arms. One arm binds to the tumor cell, and the other one to the T cell. So basically, it brings T cell and tumor cell together. It enriches T cells in the tumor. They're called bispecific antibodies. A specific subtype of them are called BiTEs, which is easier. So I'm going to talk about BiTEs. Both of them are very successful in lymphoma therapy, where we have good epitopes to target, CD19, CD20. They're selective on these tumors, and we can target them. We can wipe out B cells. So very successful. I'm going to talk about the bispecific therapy today. Just to show you how effective it is, this is a waterfall plot, and every bar that goes down is a patient that had either a complete response or close to a complete response. This is a very powerful treatment for lymphoma patients. And again, you only have like 5 or 10% of patients who either don't respond or relapse from the treatment. We're coming in lymphoma, we're coming very close to curing that disease with these new immunotherapies, with CAR T, with bispecifics. But you still have these 5, 10%, and you would like to do something about that. So CAS looked in detail at the patients who do not respond. And he looked at gene expression patterns in lymphoma cells from either patients who progress on the left side, PD, meaning progressive disease, or patients who responded, CR, meaning patients who had a full response. Yeah, there's a lot of changes, and for various reasons, researching literature and thinking about the data a little harder, we decided to focus on a gene I highlighted in red here. It's a MAP kinase that is upregulated in tumors that don't respond consistently, and there's some idea to think that it might have something to do also with PD-1 responses and with sensitivity to immunotherapy. So it's a kinase. It's upregulated in tumors of patients who do not respond to biospecific therapies. How can you ask whether this is just a correlation or if it's real? Well, you engineer a tumor and you test it in a mouse. So CAS engineered tumors that overexpress this MAP kinase, and you see the blue line, they're treated with the bispecific antibody as the dose above. Blue line, bad survival. Black line, they respond much better. So we think this is one gene that is sufficient to make tumors resistant to this therapy. Now, we do have great drugs for kinases, and there is a drug not for this specific kinase, but for another kinase in the pathway, and that drug is called ralimetinib. So we asked, well, what happens if we inhibit this kinase? And in fact, the survival curve goes up. So there's a great synergy in lymphomas in animals between the bispecific antibody therapy and adding a conventional drug, a kinase inhibitor, to this. Now, clinically, this drug, ralimetinib, is basically discontinued. People are not developing this drug. We would argue, based on this data, one should take a second look, especially in the context of these immunotherapies. It seems to be a way to make the treatment of these lymphomas better. Okay, I told you I'm going to tell you 3 stories. The third one is Ana Cadet Portolina. I skipped her first last name. Portuguese, my lab is a little bit like the United Nations. We have people from all different countries. This is New York. And her project concerns targeting a different immune checkpoint. And here I'm getting out of my depth because I am not an immunologist. We worked on this checkpoint HVM and BTLA in lymphomas, and we worked on this because this gene HVM is mutated in about 50% of follicular lymphomas that we're interested in. If a gene is mutated in 50%, you start to think about really hard what it is doing. And we wrote, I think, a useful paper about the mutations in this gene HVM, and we've understood what it is doing in lymphoma cells. It's very interesting. It has 2 functions. It inhibits the proliferation of those lymphoma cells, but it also talks to the immune system. And it talks to lie about it. It's a complicated thing. It can bind to two different types of receptors. Receptors that can be activating or receptors that can be inhibitory. It's a bit similar to the interaction of PD-1 and PD-L1. And our thinking here is, well, this interaction is great, but what about if there is another immune checkpoint? So just briefly to get to this. The key interaction is HVM expressed on a tumor cell can bind a receptor that's called BTLA. BTLA stands for B and T lymphocyte attenuator, meaning BTLA is an inhibitory receptor on immune cells. Therefore, we think HVM talking to BTLA is an immune checkpoint, just like PD-L1 talking to PD-1 is an immune checkpoint. HVM on a tumor cell talks to a T cell that has BTLA, and that T cell goes to sleep. Good. So we thought, okay, let's try to target this interaction. We tried it in two different ways by targeting BTLA, which for reasons we don't understand, never worked, but we had success in targeting HVM. And specifically what we're doing is we work on something called nanobodies. And just for background, llamas, camels, and sharks make this very specific type of antibody. It's a very small antibody fragment. It's basically just a light chain and doesn't have the Fc part of an antibody. They have certain advantages. They're very easy to make, they're very cheap to make, and it's very easy to engineer them in any form that you want if you want to make multimeric molecules and so on. And we have the right collaborators to do it. So we decided to work on llamas. Our collaborators, Rockefeller University, they immunized llamas with HVM to make those nanobodies. And llamas turn out to be easier to work with than camels or sharks. So that was a big advantage. Now, we actually identified then several high affinity nanobodies, about 15 that high affinity bind to HVM. And then we said, well, these receptor interactions are so complicated, we need a second step. We want to filter out those nanobodies that actually activate T cells. Because depending what receptor HVM talks to, it can either inhibit them or it can activate them. So we want something that has the specific effect of activating T cells. And we built this two-cell reporter system there. On the top, you have a cell that expresses HVM. And at the bottom, you have a cell that expresses BTLA, and that has a reporter, a luciferase. So if in this interaction, HVM, and the nanobody blocks the interaction of HVM and BTLA, we expect that the light comes on. Luciferase comes on, it should become visible. And that's the case. We see this, and then we engineer trimeric versions and so on and so forth. So we selected things that have a high affinity, and they're able to activate T cells. Now, do they work? We tested in different models. This was the most aggressive and the hardest to treat. And in fact, this is a model that doesn't respond well to PD-1 antibodies. These are B16 melanoma cells injected into the tail vein of animals. They go to the lung, and the mice develop these nasty lung metastases. You see in red, you see the tumor cells. So on the one side, you have untreated, and day 27, all of them have a lot of these lung metastases. With our nanobody, well, we don't get rid of it. We cannot cure these mice, but we delay the development of these metastases. The mice have a survival benefit. So we think it's a significant additional immune checkpoint similar to PD-L1, PD-1, and we would like to develop that further in the lab. In fact, we're testing combinations of targeting both of these checkpoint inhibitors. All right, that's really what I wanted to tell you. And I think the point is, for me, immune checkpoint inhibitors, anti-PD-1, anti-CTLA-4, has kind of changed the way I think about treating cancer. It's a completely new method of doing it. In my lab, we want to understand how cancers try to escape, because I think that tells us how we can make these therapeutics better, combinations, diet, other checkpoint inhibitors, and so on and so forth. Kenji, CCII, very interested in the immune cells and how these are now our allies in many ways. How can we help them? How can we make them better? And a final question, we're interested in how does this combine with existing therapies? I showed you this kinase inhibitor as a way. How does it fit into what we are using for the last 50 years to treat cancers? How does it fit into the bigger picture of these therapies? Okay, and this is basically the lab. I want to thank my collaborators, CCI, Tasuku Honjo, Sidonia, who always very generously invites me to conferences in Kyoto, where I love to go, Kenji, and this is the lab. And as I told you, we're a bit of the United Nations. Thank you very much.
Well, thank you very much, Dr. Wendell, for sharing 3 research projects at your international lab in the US. So please give another round of applause for the 2 speakers. The development of cancer immunotherapy is already changing the lives of many patients. Numerous cases have been reported in which patients with advanced stage cancer and one previously considered incurable extend their lives for a long time or even recover fully. We'd like to share a video with a message and letters from patients who recovered from the disease through cancer immunotherapy. We hope you can find a real impact. We hope you can find a real impact of the cancer immunotherapy developed by Dr. Honjo that actually saves lives.
私京都大学の病院でお世話になっております患者の浅井と申します。よろしくお願いします。本庄先生、本日は本当にありがとうございました。先生が研究開発されたがん免疫治療のおかげで私は命を救われました。私は2024年に進行した肺がんが見つかり、その時にはもう9センチの大きさになってたんですね。ですから手術もできないと言われまして、もうダメかなと思ってました。でもそれで京都大学病院を紹介されて免疫治療のお薬を飲むことになりました。その薬が私の命をつないでくれました。本当にありがとうございます。今では完治し、もう奇跡だと言われてるんですけども、本当にその大きかったがんが小さくなって奇跡というしかありません。先生のおかげで家族と一緒に穏やかな日常生活を過ごしております。もし先生の研究がなければ今の私はここにいないと思います。どうかこのがん免疫の研究がこれからも続き、さらに多くの患者さんの命を救ってくれることを心から願っています。本当にありがとうございました。
本庄先生、現在再発の兆候もなく元気に日々を過ごしております。 このような穏やかな日常を取り戻せたことに心より感謝を申し上げます。先生にお礼をお伝えしたくお手紙を差し上げました。私は2023年に進行したがんと診断され、京都大学病院で治療を受けました。初めの治療が奏功せず苦しい時期もありましたが、先生が研究された免疫療法の薬により幸いにも大きな効果を得て根治に至りました。このかけがえのない日々は先生のご研究の賜物と深く感謝しております。いただいた時間を大切に、これからも一日一日を大切に生きてまいります。先生のさらなるご研究のご発展とご健勝を心よりお祈り申し上げます。
Thank you for your attention. As you have seen today, cancer immunotherapy is saving lives and bringing new possibilities to patients who once had few options. Now, Kyoto University CCII is moving toward the next stage, controlling cancer. We have set a bold vision to control almost all types of cancer by 2050. And we are working tirelessly toward the goal. This goal can't be achieved by Kyoto University CCII alone. It can only be realized through the support of those who share our mission. To date, we have received unwavering support from many leaders, including Mr. Tadashi Yanai, founder and CEO of Uniqlo, and corporations such as Bristol Myers Squibb. Mr. Yanai, in particular, has recognized the significance of our work early on and has provided continuous support. We would like to invite you to be a part of this meaningful endeavor. We greatly appreciate your support. Donations can be made via the QR code or our website. We accept donations in various forms, including online donations, cash, stocks, and cryptocurrency. For those residing in the US, tax-deductible options are available. Your support will be a driving force to advance research and save more lives. We hope to build a future with improved treatment to control cancer together with all of you. Having said that, I'd like to invite Myriad USA, who has generously provided today's venue. So thank you so much for that. And Ms. Lee from Myriad USA will provide further details on how to make a donation.
Well, good morning, everyone. Welcome to Myriad USA. What a truly honor to host all of you here, Professor Chamoto, Dr. Wendell, and the Kyoto University friends from all over. I know some of you actually just flew in from Japan and even from Australia. So a very warm welcome to all of you to this great morning in New York. My name is Lee Chuan, and I am the Director for Asia Pacific at Myriad USA. Just a quick word about us. Myriad USA is a public charity based here in the heart of New York. We are a few blocks away from Times Square, a very privileged location to be in. We support US donors to give overseas through donor advised funds, legacy funds, gift of arts, but more importantly, we support over 1,600 organizations all around the world. We act as their fiscal sponsor in the US to receive tax-deductible funding from their US donors without having to set up their own entity. So one of those example partnership is with Kyoto University, one of our really esteemed partners for a very long time. So just last year, Myriad USA facilitated over $195 million to over 1,000 partners across 103 countries. So just a quick word about the scope and scale and what we do to our partners and to our to organizations all around the world. Now, through this mechanism of an American Friends Fund that we set up for Kyoto University for supporters who are, want to support the courses and the research and the amazing work at the university, you can provide online giving through their dedicated page on every.org, which is our technology partner, to facilitate funding from credit card, cryptocurrency with your digital wallet. But there are many different ways that US donors can support this tremendous work through obviously cash and check and direct transfer, which is a common way, but also appreciated assets such as stocks, mutual funds. We can facilitate funding from retirement plan, insurance, life insurance, etc. So all of these ways of giving here, you can find them on this QR code, and just get in touch with our team here at Myriad USA. I have my colleague Aaron sitting in the back there, but we have a whole team to support your donors, Kyoto friends and supporters to support this work. So again, just a very, very warm welcome. Thank you for spending the morning of your weekend here with us. And it's truly an honor to be partner with the university.
Thank you, Ms. Lee. And additionally, we would greatly appreciate if the media members joining us today could share this information with a wider audience. We hope you engage with us in a way that's most suitable for you. So finally, we'd like to open the floor for a brief Q&A session. Due to the time constraints, we'll prioritize questions from our online participants. Please share questions through the Q&A function of the Zoom. We'll try to answer as many questions as we can. And for those here in the venue, our speakers will be available after the event concludes. So you can ask the question after that. Thank you for your understanding. So let me check the Q&A box. Now we have 4 questions and 1 comment from our audience. The first question would be, if previous immunotherapies have failed and TKIs have failed, is it likely that further immunotherapy will also fail?
Yeah, TKI failed, TKI alone. Even TKI failed, immunotherapy could work. And there's combination therapy also applied of the PD-1 blocker therapy and TKI. So, but that depends on the tumor types. Yeah. If that is approved, that means there is chance to work. So this is the answer.
Do you have something to add, Dr. Wendell?
Well, there's so many different types of TKI and immunotherapies. So I think if one of them has not worked, I think there are probably alternatives to discuss with the treatment team and take it from there.
Okay, thank you for your answers. Let's move on to the next question. Is the information you presented applicable to breast cancer?
So what I presented is not approved yet. This is just a clinical study, phase 1 stage. So I would like you to say, please wait. Even you cannot wait. Yeah, maybe there's different options for breast cancers now based on the immunotherapy. How about you? No. Yeah. So Guido's presentation also still it's a basic research. Yeah, we need to apply these ones to the clinical phase ASAP. Yep. Thank you.
Okay, thank you for the answer. So the next question is, a participant has a family member with both breast cancer and Crohn's disease. Are there studies on inflammation and correlation across these diseases?
So cancer always accompanied with chronic inflammation, and then cancer generated. And Crohn's disease, this is maybe, this question is also related to the IRAE, side effect of the PD-1 blockade therapy, because Crohn's disease might be get severe after the PD-1 blockade therapy sometimes. But so it's a currently these are regulated by the immune suppressive drugs, but in the future I want to prove that the type of spermidine or bezafibrate which can enhance the mitochondria can inhibit inflammation but enhance the anti-tumor immunity. But that was also in the future things. So yeah.
These are really hard questions.
Yeah, it's very hard. It's very hard. Yeah.
Move on to the next one. Okay, let's move on to the next one. Since these studies are being conducted worldwide, is there a specific demographic that is more resistant and not responding to these new therapies? This is a very good question.
So I can only talk about the things I talked about, so the biospecifics. I think there isn't really a signal, and that it's specific ethnicities who are doing better or worse than others. So those treatments seem to be very effective in that case. But PD-1, I have not heard that. I don't know. You will know.
Anything to add,
Yeah.
Dr. Chamoto?
Yeah. So we need to say, yeah, these are still underwent the clinical. Underwent. This is the basic research. So yeah, I just want to say, please wait again. Yeah. So we needed to improve. We need to make this research faster, especially clinical. So we need such a fund to do that. Yeah.
Okay, we are getting few more questions. Next one is, have any of your experiments included work on soft tissues undifferentiated sarcomas such as MFS and spindle cell? Am I pronouncing correctly? Yeah.
I think I can take that, because we actually, this is not related to what I presented here, but we do have a major research projects in the lab together with the sarcoma center at Sloan Kettering in myxofibrosarcoma, which is maybe what the question is about. We recently published a paper about this, describing a new treatment for myxofibrous, YAP and TAS-driven diseases. And the finding is that a drug that is close to getting into the clinic and inhibits a translation factor called ERF4A, is a very powerful treatment for these tumors because it blocks the tumor cell's ability to produce these YAP and TAS transcription factors. And there hasn't really been a way to target them yet, but so this may be, but again, this may be a good way to do it. It works in the lab, it works in cells, it works in mice, and we will have to see if it's going to work clinically. So there is an idea to do a clinical trial, but again, the findings were, I think we just published a paper, came out last week, I think, or maybe the week before. It's a very recent, that's our contribution to myxofibrosarcomas.
Do you have any additional thoughts, Dr. Yamato? Okay. So let's move on to the next question. Immunotherapy for metastatic castration-resistant prostate cancer. Is there any breakthrough work?
Not only these prostate cancers, but for metastatics, the PD-1 blocker therapy or immune checkpoint inhibitor should work. And also, we believe this immune checkpoint inhibitor can attack the micrometastasis that cannot be observed under the current diagnosis. And so, breakthrough work. Do you have any? No. Yeah, so I think our work, basic research, also can enhance the inhibit metastasis work. Yeah.
Thank you. And the next question is, what happens when a stem cell transplant for multiple myeloma doesn't work and you go through CAR T cell transplant after it and that doesn't work either? Was it the next step?
These are really difficult questions. I think it's probably a question from a patient. I think it's important to discuss this also with the doctors who are treating you because there's a very advanced therapeutic situation. I think Kenji and I can talk to the research that's being done in multiple myeloma, and there's some very interesting new antibodies against that disease that show great promise. And that are in the clinic. But again, this seems to be a very specific situation. I think you need to discuss with the treatment team. I think an important point to make is that the CAR T cells, the stem cell transplant, these new antibodies really all come from fundamental research over the last maybe 2 decades. And that is where we are. And this is important work that needs to be funded both here in the US and in Kyoto. Thank you.
So the next question is there a role for immunotherapy in locally advanced head and neck cancer for organ preservation during resection?
Oh, resection. So, organ during resection. During resection means a before resection and after resection. So currently, immunotherapy is applied in some cancers before the resection and also after the resection, and both work. And so, but I'm not sure that strategy is also applied now, head and neck cancer. But in lung cancer, before surgery and after surgery, works very well, and both of them prevent the recurrence of the tumors. Yeah, so if possible, I would recommend to do that.
Okay, this will be our last question, maybe. Let me check. Yes. So as a clinician, how do you balance enhancing anti-tumor immunity with the risk of worsening or autoimmune or inflammatory diseases in their patients?
I'm not clinicians, but I'm very interested in the mechanism of the IRAE, and I think the best one is to discriminate, segregate the IRAE and anti-tumor immunity, and that can be done in the future. And the balance means currently after the IRAE happens, so immune suppressive drugs was administered, but if that is too much, that also inhibited anti-tumor immunity. So the dose of the steroid is very important, but currently steroid might be too high. Yeah.
So I think I'm also not treating patients for the last 20 years, but so I think an interesting area of research may be to find ways to focus the immunotherapy on the tumor to get selectivity against tumors over non-tumors. With CAR T cells, that's an issue of engineering the right receptors. I gave you one example of the CD47 as an immunotherapy, and it's an antibody that binds everywhere in your body. But if you combine it with an antibody against the tumor specifically, CD20, CD19 antibodies, you focus the therapeutic effect on the tumor, and you decrease the off-target, the systemic side effects related to an immunotherapy. Maybe there is a lot of research needed to think of ways that we can target this hyperactivated immune response against the tumors that we want to treat and avoid off-target effects in other tissues.
Thank you very much for all the questions. Now it's time to close, but I would like to share some very heartfelt comments from our participants. Like, yeah, some of the participants felt this event is very educational and informative and bringing us hope. And also some family members are currently treated at Memorial Sloan Kettering. Yeah, so they are very appreciative of this event. And one question is about the recording of this event, and we will share the recording once it's ready. So thank you all for staying with us until the end. For the online participants, we really appreciate if you could share your feedback through the survey. It will be popped out when you leave the room. We hope today's program has given you a deeper sense of the potential of cancer immunotherapy and the significance of supporting this research. We look forward to your generous support of Kyoto University CCII. Thank you very much again for joining us this morning, and have a wonderful day. Thank you.